Hi everyone. So today we start a new chapter, and this chapter is chapter 8. It's all about sequences and series. This first lesson, lesson 8.1, is all about different types of sequences, and everything in this lesson is stuff that you have seen before, just never all at the same time or in the same place. This was all sort of scattered throughout Algebra 1, so today's lesson is really just pulling a bunch of stuff together that you've seen before. So let's start with the definition of sequence. A sequence is just a list of any list of numbers as long as it follows some sort of pattern. And so you'll see I have here an example of a sequence, 2, 7, 12, etc. And probably don't have to think too hard to come up with what that pattern is. The important thing to realize is that a sequence can be thought of as a function where the domain is the set of consecutive positive integers. And that might not sound like it makes sense at first, but remember that with a sequence, we can call this term 1, this term 2, this term 3, this term 4, and so on. Okay, and so that's what this is talking about. Consecutive positive integers, that would be this, 1, 2, 3, 4. And so the term number really is what the domain is made up of, where the range would be the actual sequence or the actual terms. Okay, so just so you know, notation-wise, how we write something like this is, for example, let's take this right here. If I want to say term number 3 is 12, I would write this, T3 equals 12. Okay? And again, thinking in function notation, the 3 would be like your input, the 12 would be your output. Okay? You'll also see it written sort of generically. T sub n means term n, where n is like a variable, so it could represent any term in the sequence. Okay? And we'll talk about some other notation pieces as we kind of move along. Okay, so we can write formulas that are either explicit or recursive. And kind of going back to this same idea up here, I'm going to take this sequence and sort of put it in a table where I'm looking at n versus the term. Okay, and n represents the position or the term number. So we have term number 1, term number 2, term 3, term 4. I don't remember how many terms I have up there, but this should do the trick. And then my actual term would be like my y's, 2, 7, 12, 17, 22, etc. So term number 1 is 2, term number 2 is 7, and so on. So the big difference between explicit and recursive formulas is explicit formulas work very hard to tie the term to the term number. Okay? So that would be a function where when I plug in a 1, I get 2. When I plug in a 2, I get 7. When I plug in a 3, I get 12. I guess I'm kind of drawing my arrows backwards here, but it ties the term number to the term. So when I put this number in, I get this number as an output. Okay? And that's just like every other equation we've ever worked with. You plug in an x value, you get out a y value. So that's your explicit formula. That's sometimes a little harder to come up with. The recursive formula is generally easier to see, okay, because the recursive formula links the terms from term to term. It says what's happening to get from term 1 to term 2 and term 2 to term 3. It doesn't really care about what term number you're at. It just tells you how to get from one to the next. So again, that's easy to see, but a lot harder if you have to go down to term 30, let's say, because if you want term 30, with an explicit formula, you just plug in a 30 and you get your term out. With a recursive formula, you have to add and add and add and add over and over again until you get to term 30. Okay? So that's really the difference between explicit and recursive, is that explicit links the term to the term number, which again, term number is represented by n generally, and a recursive formula links a term to the previous term. And in general, explicit formulas are easier to use, easier to work with, but harder to come up with, Recursive formulas are easier to come up with, but harder to use, especially for long term, especially if you want to go out, 30 terms or 50 terms or so on. Okay, so let's take a look at the example 1 here. Write a recursive and explicit formula to represent the sequence of positive odd integers. Okay, so just so we understand what we're talking about when we say positive odd integers, that would be 1, 3, 5, 7, 9, etc., etc. Okay, so let's start with recursive. And you may remember that with a recursive formula, you have to give the first term. And you do that because a recursive formula works by telling what to do to one term to get to the next. So if you don't have somewhere to start, a recursive formula won't work. So for a recursive formula, I have to start by saying my first term is a 1. And then to get to the next term, I take the previous term. Okay, so if I want term 5, this little bit of notation represents term 4. If I want term 12, this represents term 11. So this thing right here, whenever you see this, always represents previous term. Okay? And then to get from one term to the next, what's happening here? Well, you should notice that I'm adding 2 each time. Okay, so I take the previous term and I add 2, and that's how I get to the next term. And so this would be my recursive formula. Okay, I start at term 1, and then I take the previous term and add 2 to it. So again, if I want term 2, I take term 1 and add 2. If I want term 3, then I take term 2 and add 2. Okay, and so on. So there's my recursive. Let's talk explicit. Okay, so an explicit formula is going to look similar to any other equation that you've ever worked with, except instead of y and x, you're going to be using t sub n as your y and then just n as your x. Now I can tell this is a linear function because it's got a constant growth of 2, right? So I know it's going to look similar to a linear equation. And I want something where when I plug in a 1, I get a 1. When I plug in a 2, I get a 3. Where I plug in a 3, I get a 5. Okay? Now I'm going to give you just a real quick recap on this, and I'm sure we'll spend some more time on this, but you may remember from last year that this constant difference, when you're working with, this is called an arithmetic sequence, but when you're working with a sequence that's growing by a constant rate, this number here becomes your slope, and then your initial value here, this here is term 1. You want term 0 to go here for your y-intercept. And you'll see what I mean in just a second. Let's see. That's not what I meant to write. You want this to be term 0. So if term 1 is 1, if we went backwards a step, what would term 0 be? Well, if I had to back up 1 here, that would mean I'd be subtracting 2. 1 minus 2 is negative 1. So I'm going to put a minus 1 there. And then ask yourself if that works. So even if you maybe didn't understand where that came from, see if you can understand why this does work. 2 times 1 minus 1 gives you 1. 2 times 2 minus 1 gives you 3. 2 times 3 minus 1 gives you 5. Okay? 2 times 4 minus 1 gives you 7, and so on. So this here would be your explicit formula. Okay? So again, when you're writing a formula for a linear sequence, meaning an arithmetic sequence, one that grows by a constant difference where you're adding something every time, and you're making a linear equation out of that, that constant difference becomes your slope, and then your y-intercept, or your initial value is always term 0, which doesn't actually show up in your sequence, but you can get to it by backtracking from term 1. Okay? So there we go, recursive and explicit formulas. Okay. Okay, example 2. Find the 9th term of this sequence, 2, 4, 6, 8, etc. If I was doing this in class, I would just turn you loose on this one and then kind of ask you to tell me how you got your answer, because there's multiple ways you could go here. If you wanted to think about this more recursively, you could just power through. I mean, 9 terms is not so bad. You could go 2, 4, 6, 8. Let's see. 10. That 9. 2, 3, 4, 5, 6, 7, 8, 9. 4, 5, 6, 7. Yeah, I thought so. And this would be your term 9, right? So term 9 is equal to 18. Now, hopefully some of you are looking at that and going, well, gosh, I didn't have to do all of that. I just did 9 times 2. If you said that, you were really doing an explicit formula. What you were saying is that if this is term 1, and this is term 2, and this is term 3, the way I link from here to here is I just do 2 times the n value, right? I did 2 times 1 and got 2, 2 times 2 and got 4, 2 times 3 and got 6, and so on. So my explicit formula would just look like this. Okay, that's my explicit formula. And then to get to the 9th term, I just plug in a 9 right here, and I get 2 times 9 is 18. Okay, so again, and maybe even if you did it this way, maybe you didn't have to write them all out necessarily, but you could get to it one of 2 ways. You could just count up 9 terms, or you could say to yourself, well, I understand how this is related to the term number or the term position, and so I can use that to jump straight to the 9th term. Okay? Okay, onward. So I mentioned this word a couple times already, but an arithmetic sequence is a sequence that grows by addition of a constant common difference. And I put grows in quotation marks because if your constant difference is negative, you're not technically growing, you're decreasing. Okay, so it doesn't always have to grow, but you get to your next term by finding a constant difference. So really all the ones we've looked at so far have been arithmetic. Okay, and arithmetic sequences, by the way, are also always linear. Okay, so their explicit formulas are always going to look like a linear equation. Okay, so in general, the recursive formula for one of these is you're going to give term 1 equals something. Okay, and then term n is always going to be found by taking the previous term and either adding or subtracting some constant difference. And again, this common difference, by the way, is always represented with the letter D. You may have seen me use that on the previous page. But so you're always taking the previous term and adding D to it. Okay. Now, for the explicit formula here, there's kind of 2 ways to think about it. What I did on the previous page was I just sort of reasoned through it, but there is technically a formula for this. The explicit formula is always found by taking, whoops, that should be term n. If you take term 1 and add n minus 1 times d. Okay? That might seem arbitrary. Okay? If you're going to memorize this as a formula, this is the thing you need to know. Okay? But let me show you what happens here. Is if I were to distribute this d in here, I get term 1 plus n times d minus d. Okay, this n times d, if you think back to the previous example we did, this one right here, n times d, our constant difference was 2. That's because this is really my slope, right? The d is really my slope. Okay, so if you're thinking linear equation, this right here is just whatever your constant difference is times n. That's like the mx in a linear equation. Now look at this. This is term 1 minus d. And term 1 minus d really takes you back a step to term 0. That's what I was babbling about on that other page. Okay, so when we did this, when we took a step back from 1 to negative 1, what we really did was we took term 1 and we subtracted d, right? And that's what this formula does, okay? So I'll be honest with you, I very rarely use this formula, okay? I always just do this. I always say term n is equal to d times n, okay? Which in linear equation forms is m times x, slope times your independent variable, plus term 0. Okay, and again, you have to do a little bit of work to get to term 0, but it's never difficult, right? So you're welcome to use this or this. This one makes more mathematical sense to me. This one is more straight memorization, but whatever one works for you is fine with me. Okay? Okay, so looking at example 3, what term is 344 in the arithmetic sequence, da da da. Okay, so what term means I'm solving for n here? And I certainly don't want to do this recursively. I mean, I suppose I could. I can see right here that this is increasing by 7 each time, right? So I could keep adding 7 and adding 7 a gajillion times until I get to 344, and then I'd have to figure out how many times did I add 7. So what term am I actually on? Okay? I would probably prefer to do this with an explicit formula. Okay? So if I'm writing this in terms of an explicit formula, I'm going to go with my formula here. I know it's going to be d times n plus term 0. Okay? Well, let's think about what we know. We know we want the term to be 344. We're trying to find term 344 in this sequence. Okay? We know our d value is 7. Remember that plus 7, that's your d value. N is what we're solving for. I want to know what term is this. And then term 0 would be if I took a step backward from 8. Okay, if I went to the term that would come before 8, which would mean that I'd be subtracting 7, my term 0 here would be a 1. Okay? And so I end up with this, 344 equals 7n plus 1. Subtract 1 from the other side, so I get 343 equals 7n, and then I do believe that is going to be 49 when I divide by 7. So it's the 49th term is what we just found. Again, that'd take a long time if you were doing it recursively. Okay? Now, if you're still kind of fighting me on this formula, if this formula freaks you out, let's show what this would look like if we use the official book formula here. Okay? So term n would be 344. Term 1 would be 8. N is what we're solving for. Okay? And then we know our d value is 7. Okay, so again, this is using the book formula. So then I would distribute my 7, so I get 344 equals 8 plus 7n minus 7. Then I would combine my 8 minus 7, and I end up with 344 equals 7n plus 1. And gosh, that looks familiar. Isn't that what I had right here? Okay, so 344 equals 7n plus 1. And then from there, I'm going to solve it exactly the same way. Okay, so again, you can use my sort of, put together formula here, or you can use the formula straight from the book. Doesn't matter to me. Okay. Example 4. Write the first 3 terms of the sequence defined by a sub n. A sub n is the same as t sub n. That just represents an arithmetic sequence equals 27 minus 4n. Okay, so the first 3 terms means I want a1, a2, and a3. And this right here is an explicit formula. Okay, it doesn't give me the 2 parts like a recursive formula. It doesn't define anything based on the previous term. So it is explicit, which means when I want term 1, I'm plugging in a 1 for n. So I'm going to go 27 minus 4 times 1, and I get 23. To get term 2, I'm going to do 27 minus 4 times 2. That's 27 minus 8, which is 19. And then 27 minus 4 times 3 gives me 15. Okay, so there's my first 3 terms. That's what this first part wanted. And then let's write a recursive formula. So remember, a recursive formula has to give you the first term. If I ask you for a recursive formula and you don't give me the first term, you will not get full credit for that question. Okay, so term 1 is 23. I already knew that. Term n, and remember we want to think about what happens to the previous term to get to the next term. So how do we get from here to here to here? Okay, well, we're subtracting 4 each time, right? We're going down by 4. So we're taking the previous term and subtracting 4. Okay? And by the way, I should have been able to tell that just from looking at this, right? That my slope in an arithmetic sequence is always going to represent my constant difference. Okay? So right there I should have been able to tell this is going to be minus 4. By the way, I'm a little bit lazy as a mathematician here. I don't hardly ever write this, but I probably should. In the book, when you see these recursive formulas, you'll always see it says something like for integers n greater than or equal to 2. Don't let that freak you out. Remember, n just represents your term number, okay? So this is saying that you can use this rule starting at term 2. And your term numbers are always integers, right? Because that's how you don't find term 1.3. So term 1, term 2, term 3, term 4, and so on. This is just saying that starting at term 2, this is how you would get all of your subsequent terms. Term 1 is already given to you, so you don't have to worry about term 1. Okay, but starting at term 2, this is what you would do. Okay, so just don't let that freak you out if you see it. Okay, I think we're on to geometric sequences, right? Yes, we are. Okay. So to counter what we just did, we just talked about arithmetic sequences. Now we're talking geometric sequences. Geometric sequences are sequences that grow, and again, it might not actually be growing, it might be decreasing, by multiplication of a constant common ratio. And for that we use r. And if you're multiplying over and over again, that leads to an exponential function. So whereas the other ones were linear, these ones are going to be exponential because you're multiplying over and over and over again. Okay? So the recursive formula for one of these things, you're still going to give term 1. Term 1 equals something. Okay? And then term n is always going to be defined by taking the previous term and multiplying by your constant ratio r. Okay? So you're always taking the previous term and multiplying by something. Okay? Okay. For the explicit formula, and again, I'm going to kind of show you what the book says and then show you where that comes from. To find the explicit formula, it's going to look like an exponential function, just like the other one looked like a linear function. You're going to have your term 1, okay, times your ratio to the power of n minus 1. Okay. Oh, I'm sorry. I shouldn't have used A1. I should have used T1. I knew something looked wrong there. So you take term 1 and multiply by your ratio n minus 1 times. Okay. Now that n minus 1 might be throwing you off, but you'll notice that the other formula had an n minus 1 in it as well. Okay. I would probably say, because you know how I like my term zeros, my way of writing the same formula would be take term n and multiply by term 0, or take term 0 and multiply by your ratio n times. Okay? Now there's a difference here. Term 1, term 0. I'll show you what I mean by that. Let's suppose you've got a sequence. I'm just going to make one up real quick. 2, 4, 8, 16, 32, and so on. Okay? If you wanted to write this with an explicit formula, first of all, your constant ratio here is a 2, which I hope doesn't confuse you because your first term is also a 2, but I think you can follow me okay. Okay, so your constant ratio is a 2, right? To write this, I would go 2 times 2, but then here's the thing you want to look out for. If I want to get to term 2 from term 1, I only want to multiply by 2 once, right? But if that's term 2, if I were to plug in a 2 and this was just an n, that would tell me to multiply by it twice, right? That's why you need the n minus 1, okay? So if I want term 2, I would take my first term and multiply by 2 one time, okay? If I wanted term 3, I would take my first term 2 and multiply it by my r value 2 twice, okay? Because that's how many jumps it takes to get from one to the next. So if I wanted to get from this term to this term, I would multiply once, twice. So even though you're looking for term 3, you only actually multiply twice. And that's why you have this n minus 1 in here. Okay? You could also use term 0, which works the same way. If you're multiplying by 2 over and over again here, to get back to term 0, you would divide by 2. Sorry, I'm squeezing that in there. Your term 0 here would be a 1. So I could write this same formula, and I could say term 2 comes from taking 1, which is term 0, and multiplying it by 2 times. Okay? And if I'm starting at term 0, then that is the correct number of jumps, right, to get to term 2. So I don't care if you start at term 1 or term 0. But if you start at term 1, just make sure that up in your exponent you've got an n minus 1. And I think we're going to practice that enough to make it hopefully less confusing. Okay? Okay, so example 5. We've got this sequence, 4, 6, 9, 13.5, 20.25, etc. I want to know, is this geometric or arithmetic? Well, really what I'm asking you there is, am I multiplying or am I adding to get to the next term? Well, you can see pretty quickly that you're not adding, right? Because to get from here to here, you would have to add 2, but to get from here to here, you would have to add 3. Okay? So I know that it's not arithmetic, so it must be geometric. The way I can check is I can ask myself, 4 times what would give me 6? Okay? Well, if I divide by 4 on each side, divide by 4, I get that r is equal to 1.5. For it to truly be geometric, that's got to work with all of my pairs of numbers, but I don't have to check all of them, probably just one more pair. So I want to know, does that hold true to go from 6 to 9? Is it true that 6 times 1.5 equals 9? Yes, it is. If you really needed to check, you could do this. 6 times r equals 9. Same thing we did a second ago. You also get r equals 1.5. Okay? So this is a geometric sequence because your terms are growing by multiplication. Okay, so let's write a recursive formula. So, remember I always have to give term 1. Term 1 is 4. And then to get to my next term, I take the previous term, and we just discovered that my r value was 1.5, so I take the previous term and multiply by 1.5. Okay? I guess to be mathematically correct, I should say 1.5 times previous term, but either one of those will work. And then an explicit formula for this sequence. I'll go with the one out of the book just so we're not confused. But so to get to term n, I'm going to take my first term, which is 4, and multiply by 1.5 n minus 1 times. Okay? And again, the reason for that is, like, for example, to get to term 2, you only actually multiply once. To get to term 3, you only actually multiply twice. To get to term 7, you would be multiplying 6 times, and that's where the n minus 1 comes in. Okay? Okay. One more example, and then we're done here. Suppose a model train valued at $2,000 is increasing by 5% in value each year. Okay? Give its value the next year. Okay? Well, to increase 2,000 by 5%, remember, I really want to think of this as 105%, which would be 1.05 as my r value. Okay? So 1 year from now, it's going to be 2,000 times 1.05. Okay? Oh, let's see. I believe that's going to be $100. That 5% growth should be $100. So it's going to be $2,100. Okay? Give the value of the collection 10 years from now. So here's why I went through all that spiel about term 0 before. Because technically, if this is my current value, this is term 0. Because this would be considered year 1, right? If it goes up, if this is what it is 1 year from now, this would be year 1 or term 1. So this formula, if I use the $2,000 in my formula, I want to consider that to be term 0. So I'm going to say term n equals 2,000 times 1.05. And this time, because I do want to make 10 jumps from this 2,000, I want to take 2,000 and go up 10 times. I'm not going to fit 10 in here. Oh, so close, so close. This would be year 1, year 2, year 3, year 4, and so on. I do actually want to make 10 jumps here. I would go to the power of 10. So the reason I didn't have an n minus 1 is because what I started with was term 0, not term 1. Okay? If you had me for Algebra 1, you heard me rant all about this last year. Oh, let's see. I don't have a calculator here. All right, well, instead of wasting your time digging for a calculator, I will just tell you whatever that comes out to be in your calculator is what that should be. There's a good math teacher answer for you. But you would just type it in exactly as this is written. Okay? Okay, so for tonight, I do just want you to give Lesson 8.1 a try. We'll be sure to go over this homework when you come in tomorrow. Homework is on the backboard. It's from the book. And again, this is all stuff that you've seen before, but again, I don't think you've ever seen arithmetic and geometric sequences mixed. So that's really what we're practicing here. We'll talk more about this tomorrow, and then we'll move into our next lesson. Okay? But I do expect to see an attempt at this assignment tonight. Okay? Have a great day.